I bought this repossessed Bugatti Veyron with supposedly a broken gearbox. Nothing happens if I try to go into drive. Nothing happens. But we managed to solve the problem with just a tiny fuse.
The $20,000 service bill became the center of attention long before the deeper engineering story appeared. Most people hear about hypercar ownership and imagine speed, luxury, and performance beyond ordinary machines. They think about massive engines, rare materials, limited production numbers, and the prestige that comes with owning one of the most exclusive vehicles ever built. But ownership at that level brings another reality that many people outside the hypercar world never fully understand. Maintenance becomes part of the ownership experience, and in some cases, maintenance costs can surprise even wealthy owners. When discussions began surrounding a Bugatti Veyron service invoice reaching around $20,000, people naturally focused on one question: where does all that money actually go? A normal vehicle owner might pay hundreds for yearly servicing. A premium luxury owner may pay thousands. But when maintenance numbers climb into five figures, curiosity grows rapidly. People begin asking whether they are paying for specialized engineering, rare components, labor expertise, brand exclusivity, or something else entirely. That question became much larger when Matt Armstrong's Bugatti project started uncovering details hidden deep inside one of the world's most famous hypercars. The story did not immediately begin with engineering mysteries. It started with ownership costs and service expectations attached to a machine built to perform at a level very few cars in history could match. The Bugatti Veyron entered automotive history as something extraordinary. It combined extreme horsepower, advanced aerodynamics, massive cooling systems, and technology designed to support speeds that pushed engineering boundaries. Creating such a machine required solutions beyond what ordinary performance cars needed. Every system needed precision. Every component needed reliability. Owners understood that maintaining such complexity would never be cheap. Expensive tires became part of public discussions. Specialized servicing became expected. Complex drivetrain systems required expertise unavailable at ordinary repair shops. Over time, the idea of massive Bugatti maintenance bills became accepted as normal reality within automotive circles. People simply assumed high costs automatically meant rare components and highly specialized work. Few stopped to question the details hiding underneath individual line items. Few examined exactly what parts were being replaced and why replacement schedules existed. That changed when closer examination began revealing something unexpected beneath routine servicing procedures. The annual maintenance schedule contained replacement items that seemed unusual. Certain components appeared repeatedly, year after year, service after service. Owners paid invoices because they trusted manufacturer recommendations. That trust exists across the automotive industry. People assume manufacturers understand their products better than anyone else. If replacement schedules exist, owners usually follow them without asking deeper questions. Hypercar ownership often strengthens that trust because owners believe extraordinary engineering requires extraordinary maintenance practices. The $20,000 service bill therefore represented more than labor and parts. It represented confidence in factory knowledge, confidence in specialized expertise, confidence that expensive maintenance existed because extraordinary engineering demanded extraordinary care. Then deeper investigation introduced uncertainty into assumptions people rarely questioned. One discovery created discussion far beyond simple servicing costs. Questions appeared surrounding whether every expensive replacement reflected exotic engineering or whether some decisions involved practical compromises made years earlier during development. Large manufacturers often share components across multiple vehicles. Automotive companies commonly reuse existing technology where it makes sense financially and mechanically. Doing so reduces development costs while improving reliability through proven systems. Many enthusiasts understand this reality. Performance vehicles sometimes contain switches shared with ordinary cars. Luxury brands sometimes use components originating elsewhere inside corporate groups. But discussions changed dramatically when people started examining whether critical Bugatti systems relied on solutions that looked surprisingly familiar beneath expensive service schedules. Suddenly, the $20,000 maintenance invoice no longer represented only cost. It represented mystery. It represented hidden engineering decisions. It represented a deeper story involving design choices made years earlier that could shape ownership experiences decades later. The service bill transformed from a simple number into the starting point of a much larger investigation. That investigation would eventually challenge assumptions surrounding hypercar ownership, maintenance philosophy, component sourcing, and the balance between engineering excellence and practical manufacturing decisions. For many viewers watching events unfold, the story became fascinating precisely because it combined two worlds rarely connected publicly. Extreme automotive luxury met ordinary engineering realities. Premium ownership met practical design compromises. High technology met surprisingly familiar components. And at the center of everything sat one powerful question. What exactly were owners paying for when yearly maintenance costs reached $20,000? The deeper investigation began when attention moved away from the invoice itself and toward the machine sitting behind it. A service bill only tells part of the story. Numbers on paper do not explain engineering decisions, component choices, or the realities manufacturers face when building extremely limited production performance vehicles. To understand why certain maintenance procedures existed inside the Bugatti Veyron ownership experience, people first needed to understand what kind of machine Bugatti engineers were trying to create nearly 2 decades earlier. The Veyron was never designed to compete with ordinary supercars. Its mission was much larger. Engineers were attempting something automotive history had rarely seen before. They wanted extreme speed, everyday drivability, luxury refinement, reliability expectations beyond traditional exotic cars, and engineering capability capable of handling more than 1,000 horsepower without destroying itself under stress. Achieving those goals demanded solutions few companies had ever attempted simultaneously. Massive cooling systems became necessary because tremendous power creates tremendous heat. Complex transmission technology became essential because ordinary gearboxes could not easily survive the enormous torque loads generated by the powertrain. Aerodynamic systems needed to balance stability with top-speed performance. Tire technology itself became an engineering challenge because existing options could struggle under operating conditions the Veyron intended to reach. Building a hypercar capable of extraordinary performance required thousands of decisions where engineers constantly balanced performance, durability, packaging limitations, manufacturing realities, supplier availability, serviceability, and long-term ownership expectations. Public discussions surrounding exotic vehicles often create an image that every single component inside a hypercar must be entirely unique and purpose-built exclusively for one vehicle. Reality works differently. Even companies creating extremely rare vehicles frequently rely on existing suppliers and proven technologies whenever possible. Automotive development costs become enormous when every component starts from a blank page. Manufacturers therefore evaluate existing solutions continuously. If a trusted supplier already produces something capable of meeting technical requirements, companies often adapt proven systems rather than spending millions developing entirely new alternatives. This practice exists throughout the automotive world. Luxury manufacturers do it. Performance companies do it. Major global automotive groups rely heavily on shared engineering resources. The important question is not whether components originate elsewhere. The important question becomes whether those components properly match the demands of their new application. That distinction eventually became central to discussions surrounding Matt Armstrong's Bugatti discovery. Matt originally approached the Veyron project, expecting one problem. Reports suggested gearbox failure. On a normal vehicle, that diagnosis already sounds expensive. On a Bugatti Veyron, gearbox concerns immediately create financial anxiety because transmission systems operating under hypercar power levels involve extraordinary complexity. People watching expected catastrophic mechanical failure. They expected damaged internals, major repair bills, or hidden problems capable of transforming an already expensive vehicle into a financial disaster. Instead, the first major discovery looked almost unbelievable. A tiny fuse appeared connected to problems initially assumed much larger. That moment immediately changed the direction of investigation. Automotive diagnosis often works that way. Symptoms sometimes suggest major failures, while root causes remain surprisingly small. A simple electrical issue can disable complex systems. Minor faults occasionally imitate catastrophic breakdowns. Finding an apparently simple explanation creates relief initially, but experienced technicians understand something important. Small failures sometimes point toward deeper underlying causes. Replacing a failed component matters. Understanding why that component failed matters even more. That mindset slowly guided attention toward a system few casual observers initially considered significant. Focus moved toward hydraulic systems, helping support gearbox operation. Attention shifted toward pump operation, thermal exposure, component wear, and long-term durability under operating conditions most vehicles never experience. Small clues began creating larger questions. Why did certain wiring show unusual deterioration? Why did insulation appear damaged beyond what mechanics expected? Why would components degrade so aggressively? Engineers design automotive systems, expecting years of operation under demanding environments. Heat exists everywhere inside performance vehicles. Manufacturers account for vibration, temperature cycles, environmental exposure, and operating stress during development. When deterioration appears abnormal, investigators naturally begin asking harder questions. Those harder questions slowly transformed a repair project into something much larger. Matt's Bugatti no longer represented only a broken hypercar needing repairs. It became an opportunity to examine assumptions surrounding maintenance schedules, engineering philosophy, and manufacturer decisions made years earlier during development. The investigation moved beyond fixing problems. It moved toward understanding why those problems existed in the first place. And once that process begins, ordinary repairs sometimes reveal extraordinary stories hiding underneath the surface. As the investigation moved deeper into the Bugatti Veyron, attention slowly shifted toward a component most owners would never think about during normal driving. People notice horsepower numbers. They admire acceleration figures. They talk about top speed records and exotic materials. Very few spend time thinking about hydraulic pressure systems hidden beneath body panels and mechanical assemblies. Yet inside high-performance engineering, small systems often carry enormous responsibility. A single supporting component can determine whether an advanced machine performs smoothly or struggles with reliability problems. That reality became increasingly important as Matt continued examining what initially appeared to be a simple electrical problem connected to gearbox behavior. The more closely the system was inspected, the more evidence suggested that the failed fuse itself was only part of a much larger story. Understanding that larger story required understanding how the Bugatti Veyron transmission operated behind the scenes. Unlike a traditional automatic transmission found in ordinary passenger vehicles, the Veyron relied on advanced gearbox technology designed to handle enormous power while delivering rapid gear changes without sacrificing drivability. High-performance engineering often depends on hydraulic systems because hydraulic pressure can deliver control mechanical force quickly and consistently. In applications where precision matters, hydraulic assistance becomes extremely valuable. Inside performance transmissions, hydraulic systems help engage clutches, manage shifting actions, and maintain operating consistency under extreme loads. Those systems depend on one critical requirement. Pressure must remain available when needed. Without pressure, operation becomes unpredictable. Delays appear. Performance suffers. Reliability concerns increase. To maintain that pressure, supporting hardware works continuously behind the scenes. Pumps activate. Pressure levels rise. Systems monitor conditions constantly. When pressure falls below required thresholds, supporting components react automatically to restore operating conditions. Most drivers never notice these processes because engineers design them to remain invisible. Systems operate quietly in the background while drivers simply experience smooth performance. But hidden operation does not mean hidden workload. Some components work constantly during vehicle ownership. Every operating cycle creates wear. Every activation generates heat. Every demand placed upon supporting systems contributes gradually toward aging and long-term durability concerns. In Matt's Bugatti, evidence suggested one supporting component experienced far greater demands than many observers initially realized. The hydraulic pump responsible for maintaining gearbox pressure did not operate occasionally. It operated repeatedly. Every time operating conditions required hydraulic support, the system responded. Pressure dropped. The pump activated. Pressure returned. Driving created repeated cycles continuously over time. Even vehicle access routines could trigger system activity. Small operations repeated over years create enormous cumulative workloads. A component activating hundreds of times daily experiences very different long-term stress compared to one operating occasionally under lighter demands. Engineers understand this reality clearly during development. Duty cycle becomes critically important. Duty cycle describes how frequently systems operate and under what conditions they perform. A component functioning briefly once daily experiences very different aging patterns compared to one cycling continuously throughout operation. Heat becomes especially important when evaluating durability. Electric motors generate heat naturally during operation. Repeated activation increases thermal exposure. Components must manage temperature while maintaining performance expectations across years of ownership. Materials matter enormously in these situations. Insulation materials protecting electrical systems must survive repeated thermal cycling. Plastics must tolerate operating temperatures without hardening excessively over time. Wiring protection becomes essential because damaged insulation introduces additional risks. Electrical resistance increases. Heat generation rises further. Deterioration accelerates. Engineers work carefully to balance these factors during system design because durability expectations directly influence maintenance requirements and long-term ownership experience. Matt's discovery became increasingly interesting because physical evidence inside the vehicle appeared consistent with thermal aging concerns. Wiring insulation showed deterioration that mechanics found unusual. Materials hardened. Protective layers deteriorated. Electrical problems emerged. Those symptoms suggested exposure conditions capable of stressing supporting systems significantly over extended periods. That observation naturally created additional questions. How demanding was this pump application compared to its original design expectations? How much thermal exposure existed under real-world operation? Could maintenance schedules reflect awareness of predictable long-term wear patterns? Manufacturers routinely schedule preventive maintenance around known aging behaviors. Fluids degrade. Rubber components age. Filters accumulate contamination. Certain replacement intervals exist not because immediate failure occurs at precise mileage numbers, but because manufacturers understand long-term durability trends. Preventive maintenance attempts to reduce future failures before they appear unexpectedly. As more details emerge surrounding Bugatti servicing procedures, people increasingly question whether annual replacement schedules connected directly to predictable operating realities engineers had anticipated years earlier during development. The investigation was moving steadily toward a discovery capable of changing how people viewed hypercar servicing costs entirely. The turning point arrived when investigation moved beyond symptoms and into identification. Automotive diagnosis often follows that path. Mechanics observe failures first. Then they isolate systems connected to those failures. Finally, they identify specific components responsible for creating problems. Matt's Bugatti project slowly followed exactly that pattern. The failed fuse created questions. The deteriorated wiring created concern. The hydraulic system created technical interest. But none of those elements alone